Pleasure to be here and present our work. CRMI, Confidence-Rich Mutual Information for Information-theoretic Mapping. Robot exploration aims to control the robots to map more unknown areas and ensure other metrics, such as map accuracy, time cost, travel distance, and energy savings, involving many works. Among these works, information-based exploration methods receive much attention recently, rather than the frontier-based exploration methods, since the former ones allow faster exploration and keep effective when extended to 3D scenes, while contain much more irregular and small frontiers. The information-theoretic exploration techniques utilize accurate metrics such as mission information, MI, to construct the information reward function and choose the optimal control policies to minimize the uncertainty for both 2D and 3D maps. In this paper, we aim to provide a more accurate information function. So, what have we done? In this paper, we propose a new information theoretic metric named Confidence-Rich Mutual Information (CRMI) for robot mapping. First, as in the left figure below, we derive the principle of CRMI based on the continuous distribution called confidence over the occupancy of each map cell. Second, as in the red figure below, to achieve more accurate MI estimates, we explicitly consider more measurement dependencies using the sensor cost model (SCM) than the traditional methods. Moreover, the proposed CRMI is more expressive in the cluttered and unstructured scenes and allows for efficient exploration because of the acceptable time complexities both for belief update and MI calculation. So, what's the real motivation for this work? Let's begin with some related works. Firstly, the notable OGMI provides a new measure of map uncertainty given new observations, such as Julian and other followers' works are mainly based on binary occupancy gray map (OGM) and the inverse sensor model (ISM). They are easy to implement and relatively efficient to compute. However, these OGMI methods share many assumptions derived from occupancy grids. They overlook the measurement dependencies between map cells, leading to conflicts between map and sensor measurements. They also usually use the binary occupancy assumption, which is hard to describe partially occupied cells, leading to inconsistent inference over map occupancy in path planning. Moreover, the common used ISM has to be set manually, which narrows the performance of OGMI in different tasks. Another scheme is GPMI based on continuous occupancy mapping. GP maps capture the spatial correlations between sample points and can query map points at arbitrary resolutions, especially infer the occupancy and uncertainty of unobserved points via extrapolation. However, GPMI still suffers from expensive computational costs in both mapping and MI calculation, hindering its online implementation with low-cost robotic platforms. So, the main problem is that OGMI and GPMI methods lead to imbalanced accuracy and efficiency. Motivated by this, we aim to study further based on the OGMI. We would like to give a brief show on the proposed method. First, we extended the confidence-rich mapping for beam-based sensors. What's the confidence? As the figure below, we use a histogram to illustrate the changing of free cells belief. This non-parametric continuous distribution becomes more confident in low occupancy as more observations are received. It also captures the inherent uncertainty of estimated map occupancy. This joint probability density function can be marginalized onto individual cells and updated recursively. In this paper, we retain the independent grades assumption for grid maps, but consider the measurement dependencies between map cells using the SCM. We consider two cases, cost in the range and out of the range. The SCM can be derived by the reflection event and bouncing event. The details are omitted here. So far, how to define, compute the CRMI. In general, MI can be expressed by cross entropy and channel entropy. On the basis of information theory, we can get the CRMI using map belief as follows. The measurement prior is a little complex, so we just put the result here, which contains two parts, one for max range case and another one for the out of range case. We compute the total CRMI via numerical integration and approximation, summing each cell's CRMI to each beam, then accumulate to a scan. The algorithm on the right side shows the calculation of the CRMI. For more details, please see the published paper. Now let's discuss the simulation and the experiments results. In case A, we conduct a simulation to compare the MI based on different sensor models, that is ISM and LCM. As shown in the red figures, in the robust perceptual field, the average CRMI is about 0.55, relatively lower than ISM-based OGMI, which is about 0.7. This mainly attributes to OGMI decreases faster and converges to the relatively higher entropy rapidly. More specifically, the log-odds update pattern based on ISM will accelerate the probabilities over binary occupancy, tending to 0 or 1. This evident difference in a short time means that the distribution over each measured cell becomes more confident. Meanwhile, the marginal utility of CRMI reduces slower than OGMI, so that the conditional entropy cannot contribute to reducing more OGMI just after receiving a few observations. Instead, the calculation of LCM relies on the occupancy estimates of each cell on the beam, and the cell's belief will transition gradually based on the parameters computed by LCM rather than changing suddenly when a new measurement arrives. The measurement dependencies are embodied intuitively by the LCM. In case B, we conduct indoor and outdoor experiments using famous datasets to evaluate the CRMI's performance. CRMI shows higher accuracy and consistency in large cluttered and unstructured environments. For example, in the Intel dataset, a typical cluttered indoor scene, as the white arrows mark, CRMI surface describes much more details about the cluttered environment, such as corners, small objects, and rooms, while OGMI surface shows ambiguity and inconsistency in these areas and overconfidence in the corridors and walls, which can be potential risks for online path planners. CRMI has similar exploratory properties to OGMI. Consider a robot driven by an information-based controller. CRMI-based reward function exactly enables attractive behaviors to unexplored place and obscured space, which own higher CRMI, while repulsive behaviors to the frontiers and current poles, which own lower CRMI. This implies the robot will explore all the unknown areas actively at some time in the future. CRMI shows similar computational efficiency with OGMI. As shown in the red tables, the time complexity of the proposed CRMI is at worst quadratic about the coin size and map resolution for belief update and MI computation, respectively. The time cost of CRM is quite similar to log-odds approach in a large scene because the actual coin size is independent of map size and quite small in cluttered environments. The time efficiency of CRMI calculation is also close to OGMI since we often use small and limited integration resolution. In order to validate the practical benefit of CRMI, we compare the OGMI and CRMI information functions using the incrementally exploring information gathering method, IIG, to find the maximally informative path given kinematics constraints and the cost budget such as distance and energy. In this experiment, we use the CAVE map and run 20 offline multicolor experiments of robotic exploration. The memory results are shown in the table below and the figures at the right side. the different IIG trade paths and the most informative path marked by dark gray using OGMI and the CRMI as information functions are also shown in the upper two figures. As expected, OGMI spends less planning time because of the sparse measurements and coarse numerical resolution, and the conditional independence assumption of measurements holds in this case. The panelized IRIC denotes the average relative information gain of a new node relative to its parent node in the IIG graph over a time window, that is, information gain contribution. IRIC is non-dimensional and can be used to compare the information functions using different map representations and calculation methods. A higher IRIC value means a denser IIG graph. CRMI generates more nodes and samples, that is, a denser IIG graph and a longer path under a given budget, which implies that CRMI-based planner or controller tends to explore more space and more carefully given the budget, rather than overestimating the information gain gathered along the shorter path in the OGMI case. In other words, as the two figures below show, OGMI gain and its IRIC converge faster. OGMI owes a smaller number of samples and nodes than CRMI because considering the mapping with continuous belief in CRMI calculation results in a slower convergence speed. CRMI has more total information gain and average information gain per sample and node, which occurs with an analysis in case A that OGMI converges to a higher value rapidly, which also means that CRMI can provide subtler exploration and safe planning or navigation with map uncertainty. Consequently, we prefer to use CRMI as the information reward function in robot exploration tasks. Finally, this paper mainly contributed to a novel accurate MI metric computed efficiently for robot mapping and exploration. Simulation results show that the proposed CRMI has similar exploratory properties to OGMI, but shows higher accuracy, consistency, and good exploration performance in large, cluttered, unstructured environments. We can see that a more accurate sensor model implies a more descriptive MI in unknown areas. Future work involves a method accelerating the CRMI calculation and more field exploration experience. For more details, please refer to the published paper on IEEE Xplore. Okay, that's the end of our presentation. Thanks for your attention and welcome your questions.